Okay, let's continue. The next part is we understand the question, and then we are going to determine the minimum gradient of this sewer. First of all, we consider for the dry weather flow condition. Okay, here is the desired level for the dry weather flow of a 4 meter cube per second. Therefore, so that we need to maintain a certain gradient for this sewer, so that this 4 meter cube per second flow rate can fill up the bottom part of this sewer. Alright? Now, therefore, what the first part is we are going to determine for we know the desired flow rate of the dry weather condition. This Q is equal to the 4 meter cube per second. Alright, and for the sewer, the lower part here, let's put a small figure over there for ease of explanation. Okay, we'll have a bottom width 1 meter and the depth of bottom part, each of these is 1 meter. Okay, and therefore the flow area is equal to 1 times 1 is a 1 meter square. Okay, and this is the flow area and the vector perimeter. Okay, which create friction of the flow body. Okay, the upper part here is open to air, therefore create insignificant amount of friction for the flow body. Therefore, here is therefore the upper part is not counted. Okay, we only count to 3. The vector perimeter is 1 plus 1 plus 1. Okay, equal to 3 meter. Okay, therefore the hydraulic radius is by definition is the area, flow area divided by the vector perimeter is equal to 1/3 is equal to 0.0333 meter. Okay, and now we know the flow rate is 4 meter cube and the flow area is here 1 meter square. Therefore the velocity is equal to the Q divided by A. Okay, and then we got 4 divided by 1 is equal to 4 meter per second. Okay, this velocity a little bit fast and may induce an erosion for the sewer, unless we provide a hardened surface, a better surface treatment, so that we can minimize the surface erosion. It's also practical for some scenarios, for some situation. Okay, go back to here. Well, we know the velocity, hydraulic radius. Okay, everything ready. We now can determine the gradient required so that the flow rate can just fill up this bottom part. Alright, let's recall the Manning formula. The Manning formula is what? Manning formula here. Okay, this is the last review. Velocity equal to the coefficient multiply the square root of the hydraulic radius and the inclination. Alright. Okay, therefore now we are going to determine the inclination. Therefore, there's a Manning formula. Okay, therefore I is equal to VC square divided by the HR. Okay, velocity is 4. Coefficient, where's the coefficient? The coefficient here is hydraulic radius 1 to the power 6 divided by the Manning roughness coefficient and equal to 0.3336.02. Okay, my calculation show me is 41.63. There's a Manning, there's a coefficient. Okay, therefore this part is 41.63 square divided by 0.333. Okay, inclination is 0.0277. This is inclination, which means for each meter run, okay, this shear should drop by around 0.03 meter. Okay, this is the gradient. All right, and then the second part. The second part is for the rainfall condition, for rainy season. Now the entire shear will be filled up. For the lower part, remaining lower part is dry lateral flow rate is always there, and then the upper part of this shear will be used to carry away the rainwater. Okay, subject to the unknown depth. Okay, however, we have already determined the inclination of the shear. Okay, this inclination is 0.0277. Okay, this is the same, which is a compiled shear. We may make an assumption that this inclination applicable for the both, or the bottom part this is a constraint, so that the upper part shall follow it. Right? Okay, now in here what we have known is the design flow rate. Equal to the for the rainwater season is 16 meter cube per second. Okay. Plus the dry weather flow rate is 4. Therefore, total come up with 20 meter cube per second. Okay. Inclination remaining unchanged. And now we are going to solve for the Manning formula. Okay. The Manning formula is solve for the full balance, Q equal to the AV. Okay, we substitute the Manning formula for the velocity here. V here is C, hydraulic radius, and inclination. Okay, now we are going to formulate for this question. Now what we know, the dimension here is 3 meter, 3 meter. This three sides, both all of them are of length 1, and x1 is unknown. Okay, this x is unknown. Okay, therefore, first of all, we're going to calculate the area for the entire flow body. Area, the bottom part is equal to 1. Okay, and for this part is 3, 4, 7. Okay, multiplied by x. Alright, and then vector perimeter 1, 2, 3. 3 meter is here is a 9 meter and plus 2x. 9 meter plus 2x. Okay, according to the figure. Okay, therefore the hydraulic radius, by definition, 1 plus area divided by vector perimeter. Okay. And then the coefficient is equal to a bit complicated. Okay, or eventually we may make it simplified to 50. This part. Okay, looks terrible. Okay, now we have already know all these terms. We can substitute to our control equation. This equation, we are going to solve it. Okay, we put everything into there. Q is okay, area. Multiplied by this one. Okay, and then multiply by the 1, say 50. Okay, here is a hydraulic radius. Where's hydraulic radius? Hydraulic radius here. Okay, and inclination. Okay, and to the square root. Multiply all this equal to the total flow rate, which is 20 meter cube per second. Okay, now this equation looks a bit complicated. Okay, let's do some simplification. Here is, if we multiply to the power of 6. Okay, here is 1. You got 3. 1, 3 is 4. This is 6. Therefore, this part is 10. Okay, for this term, 6 is 1. 3 this is 4. Okay, and put this simplified. My calculation show me this part is 1 to the power of 5 equal to 13.82 multiplied by the 9 plus 2x squared. Okay, now this equation is a highly nonlinear equation. Solve it analytically is a bit complicated. It may be too difficult for us and unnecessary. Therefore, we may apply some mathematical techniques or numerical methods to solve for the x here. The one numerical method I proposed here is to use the Newton's method. Okay,